You're not going to want to miss this episode of the AI Show where we talk all about federated learning with Azure Machine Learning. Make sure you tune in. Hello and welcome to this episode of the AI Show where we're talking all about federated learning with Azure Machine Learning. I've got some special guest, Andreas Harmke. Andreas, why don't you introduce yourself and then we'll go to you, Harmke.
Yeah, thank you for having us. So my name is Andreas Kopp. I'm an AI solution architect working with our enterprise customers on interesting AI projects.
Fantastic. Harmke.
And my name is Harmke Alkemade. I also work as an AI solution architect.
Fantastic. So you are the people that actually do stuff with real customers that have real problems. I'm so glad you're here. The first question I thought we'd start with is, what is even federated learning? Why is it important? Who wants to take that one?
Yeah, I brought a couple of slides. So maybe let's first discuss the topic of federated learning, the concepts, and then we can also show a demo. So federated learning is actually a privacy-preserving technology for doing machine learning, which means that several entities, organizations can build a joint model without the need to share any training data for that. And maybe to introduce how it works and what the value is, let's look how machine learning is done today. So assume we have a hospital, a small hospital. They want to develop a machine learning model for predicting the effectiveness of a treatment, for example, or to detect pneumonia. So they can look at the training data which is available. Of course, they have patient data. But in order to really develop a good model, the data needs to be representative in terms of age, ethnic background, gender, maybe medical preconditions. And maybe based on the data, in particular for rare diseases, the model is okay, but not perfect. But of course, this memorial hospital here is not the only hospital. So there are other hospitals who have similar data and also similar problems. So it would make sense to combine the data. So an obvious way would really to put all this training data together, to pool it, and then train a joint machine learning model. And you could expect that the coverage is better. It's more training data. It's more diverse. So the overall model that would result from a joint training would likely be much, much better. But if you look in what's happening in reality, it's not happening very often. So there are often compliance concerns in terms of data privacy, or in particular in healthcare, like GDPR or HIPAA, for example. In other cases, there could also be concerns of sharing intellectual property also in other domains beyond healthcare. So this is why pooling between organizations, even though everybody agrees it would provide a lot of benefits, it does not happen. It's relatively rare. And one technology to address this problem is federated learning. So the key idea really to understand is that multiple parties, like multiple hospitals, for example, collaboratively train a machine learning model, but there is no need to share any training data for that. And the way how it works between organizations is there is a concept of a central entity, so a federated server, which hosts a global model. So this is the joint model that all participants train. This global model is distributed to all of the participants, so to the 3 hospitals here in this case. And then each of the hospitals uses only their local training data to train on this copy, on this local copy of the global model. After a training round is finished, each of those hospitals summarize the trained weights, the locally trained weights, send it back to the federated server, to the central server. The federated server aggregates all the weights of those hospitals that have been provided for building the next iteration of the model. Then it's distributed again, and the process continues in several rounds. You can do that until convergence, so until you're satisfied with the overall performance, or you can also use it in a kind of continuous training, which means hospitals are collecting more and more data over time and bring that in, so you have a continuous training in production. That's also possible. But the key aspect really is there is one resulting model which benefits from all the data, but none of the hospitals has to share any data for that. That's the key idea of federated learning.
And what's interesting is it's very reminiscent of parallelizing large machine learning algorithms, but now you're parallelizing over the data in a way that preserves the privacy of the data and the running of the actual models too. Am I getting this right?
Exactly. So there are a couple of options. The central server or the central entity could decide to deploy the model so that it can also be used for inferencing, but you can also do it on a local fashion. But for training, for privacy, the main benefit is that nobody has to share their data. It can stay local.
And the only thing that's shared are, let's just assume, the weights for whatever. Let's just say it's some kind of neural network for vision, for example. It's just the weights that are shared up and then aggregated together in whatever mathematical fashion you want to do.
Exactly.
That's cool.
Exactly.
That's cool. Is there like a use case that you're thinking of that where you're doing this?
Yeah, I mean it's very dominant in healthcare settings, for example. So we are working with a medical device manufacturer who is testing the capability, for example. And then there are also other use cases when it comes to IP protection. So, for example, a couple of pharmaceutical companies who are actually competitors also developed a joint model based on their very secret source, their IP. So in this case, it was not about privacy, more about IP protection, and even competitors work together in this use case.
That's really cool. All right, so do you have a demo that you can show us?
Glad that you ask. So this is the demo setup. Harmke is going to show you that in a minute. The nice thing, you are able to deploy a global setting across 3 continents within 30 minutes, roughly. So the setup that you can see here is automatically deployed. We are using a public data set, a chest X-ray data set from Kaggle that you can use, so you can try it out without having to provide any data, just to get it working. And in our use case, we are combining 2 technologies. So there is Azure Machine Learning, which is used to provide the necessary compute, also to provide managed data assets, and also to track all the resulting metrics of this federated setup. And we are also using NVIDIA Flare, which is one of the leading tools for federated learning, which is doing the federated learning stuff. And you can think of it as it's a library which takes care of sending all the required training assets to the participants. So the training code, for example. If you want to enhance the privacy level even further, you can add capabilities like homomorphic encryption or differential privacy. It's relatively easy if you have existing training code in PyTorch or in TensorFlow, for example, to integrate NVIDIA Flare. And it also has a nice capability that you can start with a, let's say, simulated environment on a local VM or a local machine before you deploy the whole setup to the real world distributed environment. And yeah, with that, I would hand over to Harmke to show the thing in action.
I love that. Before we get there, so this isn't like theoretical. This is actual stuff that you've deployed and have an example of.
Exactly.
Okay, so we're going to go to Harmke because I think you have some stuff you're going to show us. Is that right?
Yeah, that's correct. I can show how the demo works and maybe also how everyone can try it themselves.
Let's do it.
So therefore, I first want to have a look at the repository. So part of the medical imaging repository on Azure, we have a separate folder for the federated learning solution. And some of the files that we have in here is the configuration files for NVIDIA I will in a minute share a bit later on how the setup of this solution works. We also have two different applications in here based on the use case that Andreas shared. So it's focused on pneumonia detection using these chest X-ray images, using this public data set from Kaggle. And we have actually two different applications in here. One is a central experiment. So in this case, we do an experiment just with one client or hospital, so we can see how the model would perform using more of a classical machine learning approach. And we also have an application in here where we separate the training over the different clients. So this is really the global federated learning setup that Andreas talked about. And other than these files, what we also have in our repository is two different GitHub workflows. And this is quite interesting because this really supports in setting up all the infrastructure that you would need that runs the solution. And we also have a GitHub Actions workflow that prepares the data set for you, because we are using a normal imaging data set from Kaggle, but we are actually splitting those into 3 different data sets so we can upload them to the different clients to basically simulate this federated learning environment where every hospital would work with a different data set. So that's on the setup, and then to go a step further.
So before you go there, if I could ask a question there, if you go back to the repo. So in the repo, you basically have this ability to set everything up in multiple geos. So this isn't just like, this is me setting up the exact federated learning with 3 different geos and then the federated part. This will set that up. Is that right?
Yeah, it's correct. So the infra workflow that we have in here will deploy the 3 different machine learning workspaces for you to simulate the different clients, and also the data science virtual machine that we are using as a federated server.
I see. Yeah. So the federated server is a machine, and then there's 3 workspaces ostensibly in different regions where there's training happening, and then it's federated up through that data. Okay, cool. I got it. All right, let's take a look. Let's take a look at it.
Yeah. So what we did to prepare the machine learning workspace to basically serve as a client in this solution is that we, for every machine learning workspace, we have the Europe hospital here, we have the US hospital, and we have the Asia hospital. So those are the 3 different clients that we're working with in this case. And for every hospital, we created a compute instance in the workspace. So this will serve as a compute to train the local model. And this is also, you see that I opened a terminal here in my workspace. I initiated the communication between the server and the clients so that the server can send these training instructions to the different clients. That's basically how the solution works.
I see.
And other than setting up these computes, what we also have prepared in these workspaces is the data sets. So this is what I shared using the workspaces. We basically register a data assets in these 3 different workspaces. So we know for sure that they all have their own private data sets that they can work with. And this is just an example image of one of the chest ray images that we have in the data sets.
That's cool. And there's a data set in each region with their data held privately in their workspace.
Correct. Yeah, indeed. Yeah.
That's cool. What else do you like? I'm trying to understand how it federates the whole thing with NVIDIAflare. That's the thing that's confusing to me. How does that work?
Yeah, that makes sense. So now I shared how we do the preparation on the client side, but now let's go to the federated server.
Got it.
So for that, we're using a different interface, and we're actually going to Visual Studio Code. And in this case, you see that I have Visual Studio Code running on my local laptop, but I made an SSH connection into the data science virtual machine that we are using as a federated server. So on this server, we have cloned the repository, so the medical imaging repository with all these assets that we need to set up the solution. And here we see again this project.yaml file, which is part of the repository where we have the configuration of the overall solution. So here, this is part of the NVIDIA setup, and here we can configure where our server is located, and we also define here the different clients that we're working with. So what we're seeing here is the Europe hospital, the Asia hospital, and the US hospital, the 3 different clients. And using this configuration file and an NVIDIA command, we can generate startup packages, and these startup packages can be run both from a server and a client perspective to initiate this communication. So that's basically the preparation. Before you start your training, you first want to make sure that you have the communication established so we can send out the training instructions to the local clients and then send back the locally trained models.
Interesting. So let's see if I got this right, because like I'm understanding it now. You're using you're using the compute instances inside of each workspace as clients and servers, for example, and the federated
Yeah.
learning one, the NVIDIA one, sends out instructions to the machines locally. They do the training on their machines with the private data, and they send stuff back to that compute instance. Is that right?
Yeah, that's exactly true. So when one round is finished on one of the clients, so for example, the Europe hospital trained the first version of the local model, then these weights are sent back to the federated server. So the federated server, which is the data science virtual machine, so that's this environment, can then aggregate the different local models into a global model.
I see. And is it like just doing like a linear combination of them, or is it just something that NVIDIA takes care of?
There are different options on how to aggregate the weights. In this case, we're using quite a simple approach, but it's indeed something that NVIDIA handles for us. Yeah.
I see. And how do you set up the communication between the NVIDIA controller and then the rest of the things?
Yeah, so that's using this configuration
I see.
file. We can use a provisioning command, which is part of the NVIDIA SDK. And what is generated is basically different startup packages. So these startup packages can then be copied to the clients, and they contain a startup script. So we can use the terminal in the machine learning workspaces to run this startup script. And then that basically starts the communication from the clients to the server.
That makes sense, and this is fantastic. Anything else you want to show us, Harmke? I feel like you've given us a
Yeah.
really good picture.
Yeah, no, this is just about the setup actually. So I also want to show a bit on what the experience
Of
would be
course.
like for a data scientist who is working from a central perspective on developing these algorithms and then sending out the instructions to the different hospitals. So this is just a quick look at the training script that we have. We are training um, a a PyTorch model in this case. So you will see a training script for a PyTorch model as you would normally recognize it. The difference here is that we're also using the NVIDIA Python SDK in this case to make sure that we can send these artifacts like the locally trained models back to the server. So it's a little bit special, but for a data scientist, this training script would look quite familiar actually.
That makes sense.
And
And
then,
if I may, so I'm so glad you started down this line, because I was just so excited about everything that I didn't even think to ask. So basically, your model code doesn't change. For example, I'm a PyTorch fan, as it looks like you are too. You really don't change your code that much for your model. You just inherit
yeah.
from a different class. Is that what I'm seeing?
Yeah, so the network itself and the training instructions, they are quite normal, but there are just some specifics from NVIDIA to make sure that these the different models can be aggregated into one model, for example.
Got it.
So indeed, for a data scientist, it's quite a familiar training script to work with, I would say.
Fantastic. And so how do you put it all together? And oh, so you're going to tell us now. This
Yeah,
is great.
yeah, exactly. Yeah, so after having everything set up and we have developed our training script, then the next step is of course to start the actual training run. So for that, as a data scientist, you could work on a notebook that is in this case also running on the data science virtual machine, and then we can use the NVIDIA SDK to basically create an admin client on our server that can send these instructions to train the model. So let's go through the different steps. We first connect to the NVIDIAflare admin client running on the server. And then we can use a different command. It's the command check status, just to verify that after setting everything up correctly, that all the clients are connected to our server. So you will see a little table here where we see the different clients.
I see.
And when that they successfully connected to our server. We have 3 clients registered. And this is when we really know that we can start a training. So then we basically submit a training job to the clients. And this is just one simple command, submit job. And you do that with, as an argument, the specific application. So this is like a bundle of files like the training script that I just showed. And these instructions will then, by using this command, be sent to all the different clients to start training. After submitting the job, that's when the training will start, and we also have a command to list the jobs after they started. So here we can see, for example, that at this moment, 2 different training jobs are running for these clients. That's a bit information on how to monitor these jobs.
So just to be clear, because I want to make sure that I'm getting this, this notebook is running in the context of the controlling compute instance in the workspace.
It's a data science virtual machine
Got
in
it.
this case, so it's not running in a workspace. So the clients are running in the workspace. But yeah, this is the controller perspective indeed. Yeah.
I see. Okay, cool. So just to make sure that this isn't some local thing you're running it
No,
on
no.
the data science VM to control the
Exactly.
others. Okay.
Yeah.
This is awesome. And this is all available in the repo?
Yeah, this is all available in the repo indeed. Yeah.
Fantastic. Anything else you want to show us?
Yeah, maybe the last component to share. What is interesting is that also from a central perspective, we also have an additional workspace, which is our central workspace. So this is not where the actual training code is running that I just shared, but we are using this central workspace to centrally track the metrics that are generated from the local experiments. So this is quite interesting because even though we are not sharing the data to a central party, we can still send some metrics like the validation accuracy from the local model and send them to one central workspace in this case. So I quickly want to highlight what those metrics look like. And for that, I will compare 2 different experiments that I did, and one is a centralized run. So in this case, we only used one hospital, which is the Asia hospital. And this is where we did the experiment just to check with the full data set, what would the performance be of the model. So this is, a bit compared to traditional machine learning because we just sent the instructions from the server to one hospital to train the model. And this is what we can see here in the metrics section that we achieved, around 96% accuracy. So this is what you would achieve with the training instructions if you would just do a centralized training run. But then we can compare that to a training run that we did on multiple hospitals. So in this case, we have those 3 different private data sets, and we only trained the local models on parts of the data and then aggregated the results. And what we can then see in the metrics is that we not only have the metrics from the Asia hospital, but also here from the US hospital and from the Europe hospital. And what is interesting to see here is that the accuracy, the performance of the model is actually quite similar. So when we have the 3 separate private data sets and then do the federated learning approach to create one federated model, the performance is usually quite similar based on the distribution of the data, of course, to training a central model on the same data set. The difference might be that it takes a couple more epochs to achieve the same performance when we do the federated run, if that makes sense.
So this workspace is a central workspace where you're pushing all of the metrics out of. It's the sink for the okay. And so I don't know. Are you using MLflow or some other thing to log metrics? You just set this as the
exactly.
Okay, you just set this as the target of the MLflow. Okay, this is cool.
Yeah,
this is cool. Anything else to add, Harmke?
No, I think that's it.
And well, that's it. She says, yeah, it's actually pretty cool. Andreas, where can people go to find out more about this?
Yeah, there are two things I would like to highlight. One is our medical imaging repository, which we mentioned a couple of times. It includes a couple of interesting use cases. Federated Learning is just one of them. But if you want to try out Azure Machine Learning for other use cases, take a look, provide feedback, and also let us know what else you might be interested in. And if you are interested in the federated learning part from a conceptual point of view, so what it is, how it works, which aggregation mechanisms are available, there's also this Towards Data Science article that Harmke and I have published, which explains more the background from a conceptual point of view.
Fantastic. And I put those links below so you can see them as well. All I can say is this is awesome. Thank you so much for spending some time with me on this.
Thank
Thank
you.
you so much.
And thank you so much for watching. We're learning all about federated learning with Azure Machine Learning here on the AI Show. Thank you so much for watching, and hopefully we'll see you next time. Take care.